Hi, so we're still doing the practice questions from page 22 of the Forces section in Roy White's excellent GCSE textbook for the CA specification. Great book to get if you're on the CA spec. Lots and lots of very helpful stuff. It follows the spec very closely, tells you about all the sorts of things that you need to be aware of in that specification. So check it out if you don't already have it. And we're going to have a look at questions 4 to 7. Question 4. An aircraft sits at rest on an aircraft carrier deck. In order to lift off successfully, it must reach a speed of 75 meters per second. The time interval between the beginning of its motion and lift-off speed is 1.5 seconds. Okay, let's see what that looks like in real life. Part A. Calculate the acceleration of the plane during this time interval. So we need to make out a UVAS list for this behaviour. So U, the initial velocity is 0. V, it says it has to reach 75 meters per second. It takes 1.5 seconds to do that. We don't know how long the runway is, so we don't know S. We're trying to find A, so it's obviously an unknown. So we know U and V and T. So that's our list. And we know that A is V minus U over T. And you can see from the list that we know all the things on the right hand side, so we just fill that in. So we end up with 75 minus 0 over 1.5, and that gives us an acceleration of 50 meters per second squared. In part B, we're told that the mass of the aircraft is 22,000 kilograms, and we're asked to use our answer to part A to calculate the resultant force on the aircraft. Well, that's a mass, an acceleration, and a force. That's clearly going to be Newton's second law, F equals ma. And again, we know both the things on the right hand side, so we're just filling this in now. A is 50 meters per second squared. The mass has just been told to us at 22,000 kilograms. 22,000 times 50 is going to give us 1.1 million newtons. That's quite a force, but if you think about it, the acceleration here is massive. That's like 5 times the acceleration of gravity. So we would expect to need a fairly large force on a fairly large mass to make that happen. And I suppose it's worth watching another one, why not? Question 5a. Tim, who has a mass of 65 kilograms, rides a bicycle of unknown mass. A resultant force of 210 newtons produces an acceleration of 2 meters per second squared. Calculate the mass of the bicycle. So let's try and put down some information about what we know here. So here's Tim, and we know he accelerates at 2 meters per second squared. And we know that the mass being accelerated is his mass, 65, plus the mass of the bike. So we'll call it like m equals 65 plus b. And we know that the resultant force causing this acceleration is 210 newtons. So these are the parameters for F equals ma. 210 newtons causes him and the bike to accelerate at 2 meters per second squared. So this is obviously Newton's second law, F equals ma. So m is going to be F over a. And filling that in, we get 210 on the top line and 2 on the bottom line. And that means that the total mass is going to be 105 kilograms. And now we just remind ourselves of the fact that m is 65 plus b, which is the mass of the bike, which means that 105 equals 65 plus b. So B is going to be 105 minus 65, and the mass of the bike turns out to be a rather heavy 40 kilograms. Part B, a racing car of mass 2500 kilograms accelerates from rest on the starting grid. The engine exerts a force of 1.5 times 10 to the 4 newtons. Calculate the acceleration of the racing car. So this is straightforward. F equals ma. We're asked to find a from an F and m value. So we've got this force and this mass. And so F equals ma, a equals F over m. And just filling that in, and that gives us an A of 6 meters per second squared. And just separate that section. (6a) Calculate the weight of an object of mass 70 kilograms on the Earth. So this is just straightforward use of the weight equation, that W equals m times g, where g on the Earth we always take to be 10 meters per second squared or newtons per kilogram, depending on whether or not we've been told to do anything else. So if we're not told to take it to be anything else, we always take it to be 10 newtons per kilogram. So W equals mg, 70 times 10. And that's going to give us a weight of 700 newtons. Part B then, the same object is taken to the moon, where g equals 1.6 meters per second squared, or newtons per kilogram. So they're the same unit, remember. Calculate its weight now on the moon. So it's still W equals mg, but before g was 10 newtons per kilogram, whereas now g is 1.6 newtons per kilogram. And they say meters per second squared, but the acceleration and the force per unit mass is the same thing. Now we take our 70 and multiply it by 1.6 instead of 10, and that gives us 112 newtons. So this question's illustrating two things. One, that the mass of an object is an unchanging property, so this 70 stays the same whether you take it to the Earth or the moon. What does change is the local value of gravity in those two locations, and that alters how much it's pulled towards the ground. So part C then, on another planet, the mass of 12 kilograms weighs 105.6 newtons. Calculate the value of g on this planet. So that's just rearranging the equation with g being the subject, so g is going to be W over m. And if we fill that in for those values, we've got 105.6 divided by 12. So that's going to be like 8.8, and I was going to use meters per second squared because that was the units of g that they had used before, and then I noticed this question D comment on the units for g, and I think maybe what they're getting at here is we divided some newtons by some kilograms, so therefore we would write it in newtons per kilogram. And I think part D is about commenting on the idea that meters per second squared and newtons per kilogram are the same thing, or that g is the amount of newtons you get for every kilogram, the force per unit mass. So I'm assuming that's what they're at here, just saying that meters per second squared, newtons per kilogram are the same thing, and you can think of it as an acceleration, or you can think of it as a force per unit mass. So it's basically that these two different units are identical. I'm assuming that's what it is. That one of them represents how many newtons you get for every kilogram, and the other one represents how much your velocity will increase per second when you're accelerating. Question 7. A bullet is fired vertically upwards from a pistol from the surface of a planet. It rises to a maximum height of 1875 meters in a time of 25 seconds. Calculate the average velocity of the bullet during this time. Okay, so we've given total displacement and a total time. So that's the method here that we would use to calculate average velocity. So filling that in, 1875 over 25 gives us an average velocity of 75 meters per second. B, then, using your answer to part A or otherwise, calculate the maximum velocity of the bullet. So this is an example of a uniformly accelerated motion, and if that is the case, if this is the average of u and v, then we can write an equation that involves u and v, just the mean of them. In the case where it's uniform acceleration, where the velocity time graph between u and v would be a straight line, you can write that the average velocity is also u plus v over 2, the mean of them. We know at the highest point v would equal 0, so we know the average velocity from the first part, we know v will be 0, we should be able to find u. So 75 is u plus v over 2, and 75 just equals u over 2 since v equals nothing, so u would equal 2 times 75, which means that u was 150 meters per second. The bullet then takes another 25 seconds to fall back to the planet's surface. Part C, sketch a graph to show how the velocity of the bullet changes during its entire motion. 4 marks. So firstly, I'll just make a little bit of room here. So firstly, let's get rid of a few misconceptions about the word sketch when we're talking about sketch a graph. It doesn't mean you do some, scribbly version of the graph. It just means you draw a graph without graph paper, and you instead indicate all the important numbers on the diagram that you're drawing. So you're drawing a diagram of a graph with all the important numbers on it. So it's a good idea to think about what all the important numbers are. It starts off at time 0 with an upward velocity of 150 meters per second. At 25 seconds it's going to come to rest, and then it's going to fall symmetrically so that by the time it hits the ground it's travelling at 150 meters per second again, but in the downward direction. So we should really think about that first. So because these are velocities, we need to indicate that they have opposite directions, and so that means we make one of them positive. I'm going to make the first one positive, and I'm going to make the second one negative. So our graph is firstly going to have a steady gradient because it's a uniformly accelerated motion graph, and it's going to be 0 in the middle, starting at a positive value of 150, ending at a negative value of 150. So that makes it very easy now to draw the graph. So velocity in meters per second going from plus 150 to minus 150, time going from 0, 25, 50, those are all the important times, and it crosses the axis at 25, so it's velocity 0 there, and then it goes to negative 150 by the time it gets to 50 seconds. So the important issue here is never draw something like this until you've thought about what all the values are and what their signs are. Don't just start sketching. So D, what is the average velocity of the bullet over the entire distance covered? Two ways you can think about that. You can think about the areas as being a positive displacement and identical negative displacement, or you can think about the fact that it ends up where it started. So if you end up where you started, then a vector between your start point and your end point, which is really your net displacement, has no length because you're back where you started, and therefore your net displacement is 0. Therefore your average velocity would be total displacement over total time, which would also be 0. So your average velocity would be total to 0, and give a reason for your answer E, because you're back where you started, so your total displacement is 0. Part F, then use your sketch to determine the acceleration due to gravity on the planet. Now the gradient of a velocity time graph is the acceleration, So we've got a rise here of minus 300. It falls by 300 meters per second during a run time of 50 seconds. And so we get like negative 300 over 50, and g equals to minus 6 meters per second squared. What does that minus 6 mean? It means it points down. That's all it means. So it's a downward 6 meters per second squared. Where's the minus coming from? Well, we took the upward velocity to be positive in our graph, so g pointing down is negative. And that's questions 4 to 7 completed. 8, 9 and 10 will be done in a later video. Thanks for watching.